5 of homework 4. We are to perform a non-von Neumann stability analysis of the Craig-Nicholson method using part 4 to prove that there is indeed no constraints on the choice of dx dt with regards to stability. So let's get started. If we remember from the last part where we did a von Neumann, we used Euler's formula to substitute, get in terms of cosine, and then we solved for the value that we could use to be stable at for the explicit differentiation. Then we did the Craig-Nicholson implicit differentiation, and we got this big old formula right here. And that's the formula that we are going to be plugging in our Euler's equation into. We know, and for the stability analysis, we know that the Euler's equation can be reduced down to 2 cosine k delta x, which is what we did last time. And for this time, we need to relate the tjn plus 1 to the tjn using our little omega. That is just basically a placeholder for our Euler's cosine derivation. And we know that we have stability if our omega value is less than or equal to 1. So we want to look for that omega to be less than or equal to 1. Now I went ahead and plugged in Euler's into all of, again, I said this equation here. So that's what this is. This is just simplified of that. So on the left-hand side here, we have tjn plus 1 is equal to negative u e negative k delta x plus 1 minus 2u minus u e negative I k delta x, and then the right-hand side is tjn, not jn plus 1. And then we just have a couple switches of positives and negatives in there. So how can we rewrite this? We want this term on the left-hand side all by itself. So we can rewrite it like that. And let's go ahead and skip a step and throw in the old cosine switcheroo, which will leave us with, actually let's throw this a line lower just so we're nice and neat here. Times 2u cosine x all over and plus 2u let me just check and see if this is right real quick. I'm pretty sure this is right. I just need to be sure before moving on, and also we'll screw up everything else. Alright, I had everything right except this guy down here needs to be a negative. We can rewrite this as one minus 2u minus cosine k delta x all over 1 minus 2u plus cosine k delta x we can then say that this term here, our 2u plus or minus cosine delta x is our mu term, is our omega term rather. This is actually nice. This is our mu term, and just by looking at this, we know that this is always going to be positive. This is always positive. Because cosine can either be, the bounds of cosine are -1 and 1. And if the cosine in this term is -1, that's going to be a positive because negative and negative is a positive. And if it's a positive, it's just going to cancel with the outside. So this is always going to be positive on the inside. That's very important. So when we rewrite this, we can rewrite this as (1 minus omega over 1 plus omega). We know that the only way for omega to be equal to 1 in this is if only if this term to be equal to 1 is if omega is 0. Then this term will be 1. So the only way for this to be 1, this is always going to be greater than or equal to 1. Which is exactly what, no, I'm sorry, this right here is always going to be greater than or equal to 1, less than or equal to 1. And that will allow this term to never reach positive or negative infinity. Meaning that this will always be stable. It will never be imaginary, never be undefined, it's always stable. So we just proved that omega will always be less than or equal to 1. And that is exactly what we needed to prove when we started this problem. Per the von Neumann stability analysis, the implicit differentiation by the Crank-Nicholson method is always stable no matter what you throw at it, no matter what dt, no matter what dx. Because if we remember, u is equal to the thermal diffusivity times the time step times the change in the x value squared times 2. So no matter what the change in the time step, no matter what the change in the x, and no matter what the change in the thermal diffusivity, omega will always be less than or equal to 1. So that is perfect. That shows stability no matter what, and that is exactly what we want to see. Thank you very much.